Okay, so tutorial. So we will move on to tutorial 3, uh, electric potential. If you are given an electric field, if you are given an electric field, how do we determine whether it is an electrostatic field? So for question number 1, so you are given Roman 1 and Roman 2. So different electric field. K is a constant, obvious. So how do we know whether it is? How do we determine the whether it is a electrostatic field? How do we do that? Any idea? All right, anyone? Wrong is okay. I mean, any idea on how to determine this, whether it is a electrostatic field or not? So I'm not asking for a specific answer, but I'm asking on how. Means, is there any mathematical operation that you need to perform on electric field? I mean, I'm not asking for the full steps by step of the solution. I'm just asking for how do we proceed to determine whether the given electric field, it is an electrostatic field or otherwise. Janwai? Divergence. Okay. Ming, what about Brian? Okay, Janwai, if we use divergence, what we are expecting. So if we divergence give you a value, does this mean an electrostatic field? Or divergence equals to 0? Is it an electrostatic field? Okay, no idea. So I did mention before that if we test the curl of an electrostatic field, so the curl value will give us a 0, and the divergence value, of course, it must be some value, some kind of value. Okay. Um, so first we test using the curl of E. It must be equals to 0. If it's not equals to 0, then it is not an electrostatic field. So what I'm saying is electrostatic field. I'm not saying about other electric field. So the keyword here is electrostatic. So for electrostatic, the curl of E must be equals to 0. So we are testing this value here. So the curl, I mean, I suppose that you should know how to find this using determinant. Okay. Therefore, since um, the curl of E is not equals to 0, therefore the electric field E is not an electrostatic field. It can be an electric field, but it is not an electrostatic. So it is not an electrostatic field. So as I said, it can be an electric field. So electric field, there are two types. Um, I did mention before. So what we are studying now is only the static part. It is a static field. So that means it is a conservative field. So if it's a conservative field, that means there's no curl. Yeah. So the curl of the field must be equals to 0. And this is not equals to 0, and therefore it is not an electrostatic field. Sorry. So therefore is no. So I will leave this to you for part 2. I will leave part 2 for you to test it on your own. So let's move on to question number 2. Okay, find the potential inside and outside a uniformly charged solid sphere whose radius is r and whose total charge is q. So use infinity as your reference point. Compute the gradient of v in each region and if field check that check if the field use the correct field. Sorry. Okay. So, but the compute of the gradient part, we let's try to use the potential. How do we proceed to find the potential first? So you are given a solid sphere. Okay. So you are given a solid sphere. So the total charge. So we have some kind of volume charge density. Since it says that the potential inside and outside of a uniformly charged solid sphere whose radius is r, whose radius is r. So so this is a solid sphere. Okay. So the total charge carried by the solid sphere is q. Yeah. So that means the charge distribution is over the volume, is over the entire volume. Okay, that means it is that it is distributed uniformly over the volume for charge q. So use infinity as your reference point. So I wanted to know again, what would be your strategy to solve this? So again, I'm not asking for a specific answer. I'm asking for how are you going to approach this problem? So the information is already here. Yeah, the information is everything is already here. So uniformly charged. Okay, that means the volume charge density. It is obvious. So the volume charge density, let's say I use as rho v, the volume charge density, which is q, divided by the volume of the sphere. So the volume of the sphere is what? Volume of sphere. So coulomb per meter cubed. Yeah. So this is equals to q divided by 4/3 pi r cube, right? So that will be my volume charge density. Okay, so we know rho v. Okay, we know rho v in terms of q and r. In terms of q and r, q and capital R. So how should we proceed this? They ask us to compute. They ask us to find the potential inside the sphere and outside. We have learned everything up until this point. I mean, the knowledge that you have learned so far. I mean, from lecture 1 up until last week lecture, everything you have learned is applicable to. I mean, uh, to the exercises. So I mean, how now you have to utilize what you have learned. So anyone, how do we approach this problem? So just now I asked about Brian. Brian, are you there? Brian? Yeah. So any idea? Sorry, what you say? Sorry. No idea. Uh, okay. Meng Hang, Ziyuan, Chen Wai again. Chen Wai. Okay. So what relates potential and electric field? Yes, John. Yes. Yes, correct. We can apply Gauss. We can apply Gauss law. So when you apply Gauss law, what you determine? So you are given a volume charge density. Okay. I mean, since the question already mentioned here, the total charge is Q is distributed over the volume, right? So and we can actually formulate the volume charge density which I have written here. So given that, so we use Gauss law. So basically, we can determine what is the uh, electric field, right? So first, we will determine the electric field. So therefore, by Gauss law, so for the region R less than, for the region R greater than R, okay. So which is that means the entire sphere the entire, I mean the Gaussian surface will enclose the entire sphere. So this implies the closed surface, the entire sphere, is the volume charge density. So I will continue to write here. Sorry, maybe I just write it here better. So by Gauss law, so for the region outside the solid sphere, the flux out from the flux that coming out from the imaginary Gaussian surface is equals to the total charge enclosed. So, so we already knew if let's say the charge distribution is symmetrical, it is symmetrical. So therefore, the Gaussian surface that we apply is also a sphere. It's a spherical surface, yeah, a Gaussian spherical surface, and therefore the electric field will be perpendicular to each point of the surface. So we can straight away write this as, okay, so the r squared here, the r represent the Gaussian surface. Maybe I should include it in the diagram. So so the Gaussian surface have as a radius r, and now so here is on my left hand side. So on my right hand side now, which is the volume enclosed, I mean, which represent is the Gaussian volume, that is, I mean, the volume enclosed by the Gaussian surface. So so basically it means that it covers, it encloses the entire sphere. So the charge enclosed now will be the obvious rho v multiply 4/3 by r cubed. So therefore E, so we have rho v So rho V over, I mean, multiply with the volume. So we have Q now. So which is 4 pi epsilon naught R square. Okay. So what about inside? So for the region inside, so this is for R less than R. So the small r represent the Gaussian radius. So in this case, so on my left hand side again, it is the same. It's the same term, but it will be rho V now is 4 over 3 pi r squared, pi r cube, pi r squared, yeah. Sorry, pi r cube, sorry. Okay. Okay. So bear in mind, rho V is Q over 4 over 3 pi capital R cubed multiply 4 over 3 pi R cubed. So simplifying this, you get Q times R, 4 pi epsilon naught R cubed. Okay. So that is E inside. So if we take into account the direction, so it should be in the R cap direction. Sorry, R cap direction. Okay, so now we have determined both electric fields. So now, how do we proceed from here? So we have determined the electric field inside and also outside. So R greater than R is outside, and this is inside. Okay. So how do we proceed now to determine the potential now, the potential outside and also inside? So what would be the next step? So how now? Anyone? Yes, correct. All right, Wei. I'm not sure how you do the integral sign, but nice. Okay, so we have to determine now the potential for outside now. So, oh, sorry, potential for inside or outside also possible. So let's say we perform the potential for inside first. So V of R negative, okay, from okay, so from infinity to R, okay, to a position R which is inside the sphere. So first is from negative infinity. Sorry, negative from infinity to capital R first. So bear in mind this is evaluation of potential inside, right? So we have to evaluate. So we have to find a reference point. So the reference point which is already given to us, which is stated in the question, it said use infinity as your reference point. So we use infinity as our reference point. Okay. So the evaluation here. So as you can see, the let me just copy the diagram again. So assuming that we bring a point charge, let's say a point charge here, Q prime, let's say. We want to bring a point charge from infinity. So this is from infinity to inside here. Yeah. So what is the work done of bringing this point charge? Okay, so we want to evaluate the potential here outside. So the potential outside is from infinity to R. So we are using the electric field expression for the region outside first. So for the region outside is here. This is outside. Okay, and this is inside. Okay. So this is the expression, the electric field expression for outside. And first we have to overcome. Uh, so that means we have to do work against the electric field outside. So which is this region here. So all right. So when it reaches at the interface R, so when it reaches at the interface R, okay. So when Q reaches at the interface of the sphere, so the sphere have to go in, right? Because we are bringing in into this direction here. So that means this we have another integral which is minus. So the limit is from R to small r. So this is my Gaussian. This is my Gaussian surface. So we are bringing into this position here. So it's QR. So the first integral, the first and second integral can be evaluated easily, right? Uh, so Q 4 pi epsilon is all constant, so I can factor outside the integral. Okay, so what would be the result of integrate 1 over r squared? The variable of interest is dr, so that means it become 1 over r. So it's actually negative 1 over r. So there's a negative sign here, it become positive. So infinity to r. And similarly, so we have minus here. So again, q 4 pi epsilon r cubed. It is constant, so I can factor out q over 4 pi epsilon naught r cubed. So integrate r dr, it becomes r squared over 2. So the limit, evaluation of limit from r to r. So for the first term, you have q over 4 pi epsilon naught r. So infinity is 0, so we do not need to write here. And q over 4 pi epsilon r cubed. So this is r squared over 2 minus capital R squared over 2. Okay, we can further simplify this. Okay, we can further simplify this. So here we see that this term here, this term multiplied this term, it become q over 8 pi epsilon naught, epsilon 8q over 8 pi epsilon r, right? So is plus. Negative, negative is plus. So plus with this term. So it become 3q now. So we have 3q actually. Sorry, it's 8. Yeah, sorry. So it's 3 minus r squared over r squared. Okay, so that's the answer. And okay, so what about outside? So for the region outside now, so just simply I mean we have actually evaluated this part here. So this is q over 4 pi epsilon naught r. Yeah. So that's the potential outside the sphere. So that's the answer. And if you want to plot this, so if you let's say we want to plot this, so you want to plot the amplitude of the electric field over the distance of r. Okay. So from inside, um, so if we look at this expression, is going to be somehow like a parabola, right? So this is r squared, right? This is r squared, and this is like this is constant. R squared is the capital R squared is a constant. So the only variable here is small letter r squared. So minus r squared. So we knew that for quadratic, a positive, so let's say x squared is, it looks like this, right? And negative x squared, it looks like this. Okay. So we must, that means the curve trace, the trace of the curve may have some kind like, may have some profile like this when we sketch it. So when r equals to 0, So when r equals to 0, we start at a value yeah, so we start at this value here up until r. So when r equals to r, it is q over 4 pi epsilon naught r. So the curve profile may look something like this. So it is a quadratic. Okay. Then at this point here, starting at this point here, it goes further. It goes, it is in, because the variation, is with r, right? Sorry, the variation is with r. So the variation is with 1 over r. Then because this is now outside now, so outside it will decay further. So it will decay further. Okay. It never touch 0. Yeah, it never touch 0. Almost, but never touch. Sorry, some correction here. So as it decays, it goes smaller value and smaller value. So that's how the profile should looks like. So at the starting is 3q over 8 pi epsilon r. So how I get it? I just substitute r equals to 0. So as it approaches approaches r equals to r at the interface of the sphere, then we have r squared here. So 3 minus 1 is 2, right? 2. So 2 and 8, so become 4. So that's how I get q 4 pi epsilon naught r. Yeah. Okay. So that's all from me, because we have another 5 minutes before our next class. Before we end our session today, um, any questions? So I have demonstrated to you how we approach to determine the potential using, first we use Gauss law. Okay. There are also other methods. Yeah. Direct integration. There's also direct integration, volume integration. From the notes that you have seen, so we can directly use this as well. V rho v dv 4 pi epsilon naught r. Yeah. So r prime, maybe I just put a r prime. So this r here is inside, and this r prime represent the point outside, inside or outside. Yeah. So we can use this form as well to determine the potential. Okay. So now, since we have all the potential here, we can, in fact, we can differentiate this. Yeah, we can differentiate. Sorry, this is supposed to be r here. Sorry, what I'm doing. Okay, so now we have v. So we can, the next part of the question is saying that compute the gradient of v in each region. the gradient of V, basically we are trying to get back what is the electric field by using the gradient of V. So the electric field using the gradient of V, okay. So we can compute this. So we using this. So we have all the potential already. We have all the potential in terms of R. Then by applying the gradient, then we can determine what is the electric field inside and outside. So you can compare the the expression for E that we get using Gauss law and so on. So okay, so we'll stop here. I see you in the next class. So you can ask me if you have question, then you can ask me in the next class. Yeah. Okay, so I see you in a while.